Hello, everyone. I would like to thank all the organizing committee members for this visual conference and for accepting my paper to be presented today. My name is Ochebu Chimere Victor. I'm a master student in the Department of Energy and Petroleum Engineering from the University of Energy and Natural Resources, Sunyani, Ghana. Today, I'll be presenting on a research paper titled Modeling and Optimization of Hydrosolar Isolated Microgrid without a battery storage system, a case study of Harvard Business Cluster, Nigeria. One may ask, is it possible to have a system without a battery storage in an isolated microgrid? Well, we got some satisfying results from this piece of research. So as we proceed, you will get to know some of our results from this research work. Unreliable power supply in Nigeria has been one of the major obstacles to doing business in the country after lack of access to finance. Only 60% of the population has access to electricity, of which 80% comes from gas and oil-powered backup generators. So these conventional sources account for about 14 gigawatts of power produced from these small-scale generators. Businesses in Nigeria spend almost 14 billion US dollars annually on operating inefficient generators that are expensive, with poor power quality, noisy, and polluting. The cost of energy from these generators is about 40 US cents per kilowatt hour. Even though renewable energy resource potentials are enormous and have the potential to mitigate climate change and sustainably resolve energy crisis in sub-Saharan Africa, and in Nigeria particularly, their deployment over the years has been very slow because the cost of energy storage has been one of the major challenges stalling their development, since their variable nature requires a stabilization mechanism provided by these storage systems. To further provide stabilization, conventional energy sources continue to have a share in the so-called off-grid renewable energy system, which has made its operational sustainability and climate change mitigation an illusion. The research problem is that poor power supply has left the small-scale businesses with no option than to opt for different power generation alternatives, which are highly degrading and polluting to the environment. With this, energy supply has not been sustainably met with the best technological fit in the renewable energy space. So the objective of this research is to conduct a techno-economic feasibility study of a micro-hydro-hybrid power supply at the selected site without a battery and a generator backup. The methodology employed in this study is simple. We identified the research problem. We reviewed relevant literatures. We collected data, the river flow rates, the load demand, and solar radiation data. We size our system components and our system design using HOMA. We optimize our system, we optimize the costs and the resources. We employed a common algorithm for decision making. For our demand response, we equally use loss of load reliability measure to be able to see all the expected operational condition over our system operational life or annual operation of our system. The figure you are seeing is the average daily energy consumption used in this research. This load profile is very, very important as it peaks during the day. This is solar resource data. And the average peak sun hour from this location is above global average. The figure is the average monthly river flow, which shows the patterns of the river flow throughout the year. The table is the cost component input used in this design and simulation. The key result from this research show two categorized optimization results. The first is the system with solar, battery storage, and the hydro, which Homer ranks as the most optimal system. The second is the system with only solar and hydro. But we choose the second system as the best system, a system without a battery storage. How so? Looking at the state of charge from the figure, we see that the system with the battery storage will experience deep and extended discharges, which weakens the battery place over time. Whereas the second system is devoid of capacity loss due to degradation and corrosion of these batteries. We equally know that Homer assigns and uses round-trip efficiency throughout the battery lifetime, which is reflected on a lower net present cost and cost of energy, as we have seen in the categorized optimization results. The maintenance and operational complexities devalued the benefit of utilizing this scheme, especially for rural electrification. The choice of our consideration to equally takes into account the real-life technical and operational resilience of PV and hydro system, which provides relatively stable power to the base load, free from persistent concern around maintenance and failure rates. So the hydro provide power to the base load throughout the year. The figure on the screen is the cost optimization, is for cost optimization. When we superimpose cost of energy on the system cost rate, the effect of increasing battery storage on cost of energy is greater than the cost of PV system, which shows that generator costs are low enough relative to storage costs. So because of this, it is more valuable to add generation capacity than storage capacity, especially in a commercial load profile with a parabolic or trapezoidal load shape, just as we have in this study. Though energy storage can transform intermittent renewable energy to provide high value of energy on demand, but regrettably, cost has been a key challenge over the years. Replacing battery storage with a relatively stable hydro system reduces or eliminates this challenge. In our resource optimization, we see the months of notable solar radiation from the figure as between October to May. We can see that PV generation constitutes the major role in the overall electricity production during the periods of peak demand. So during the day, when the load peaks, the PV is available to compensate the peak load. So what happens during months when solar radiation is very low? The figure on the screen is, on the other hand, the rainy months when solar radiation are low. This is particularly for the months of June to September. The PV generation is almost negligible, particularly in the month of August, as we have seen on the figure. And the corresponding lack of energy production from PV is compensated by the hydro. So at this point, the hydro not only provide power to the peak load, equally not only provide power to the base load rather, the hydro equally provide all the power needed for the entire system. The chart is the decision tree-based demand response strategy employed in this study. A machine learning model tool is used here, which mimics the human level thinking and provides a common algorithm for making decisions. The decision tree model used here determines the available energy production for the forecasted data in Homer and compare it with the energy demand within the time period to make a decision, that's prediction, either to shade the loads, interruptible load, or have a full supply. This is represented in the internal nodes of the three branches. Again, if the load demand is greater than the electricity production, the system initializes the demand response. We equally employ the reliability measure, which looks at all the expected conditions over a whole year of the system operation. If the loss of load probability from equation 2 is 0, it means the instantaneous power generated means the required load demand. That's the instantaneous load demand. And when loss of load value is 1, it means that the required power demand is not met. So the system will try to shape the load at this point. In conclusion, this study will be helpful in balancing energy supply demand gap, especially in a commercial load profile. Instead of the sole renewable energy generation system with storage, which are common today, solar photovoltaic system, including hydro, in the midst of the hybridization, can produce reliable energy as the availability of these resources are complementary. Again, there is no optimal solution to hybrid renewable energy system design and selection due to multiple constraints. So it all depends on the model to conduct some in-depth technical details before he or she will make the final design decision. In conclusion, optimum operational reliability of a hybrid system, including hydro in the mix, is dependent on extensive analysis of river flow rate to ascertain the seasons of possible flow variation. Because the hydro in this system provide power to the base load, is the base supply. So an extensive analysis will try to look at how stable is the river flow. Can it provide stable power to the base load? So this research needs to be done before this study will be implemented. If reserve power is needed to meet short-term power shortages, an extra expenditure needs to be considered for suitable reserve with a bondage that will provide auxiliary power supply to complement supply during seasons of low inflow or low solar radiation. Demand response is essential in microgrid design due to uncertainties in supply to maintain operational reliability. End of the slide. I thank you all for paying attention during the course of this presentation. Thank you. These are some of my references.